Welcome everyone. Thank you for joining in to Bryan Research and Engineering's Caustic Treatment and Merox webinar. My name is Ganang Srivastava and I am the ProMax consultant for all our users and prospects in the Middle East and Asia Pacific region. I am joined today by a few of my colleagues, Omar Mikawi, Joachim Su, John Chan, and Dee Wu, who are also together working for the support and business development of ProMax in the Middle East and Asia regions. Today, we will be focusing on the process engineering and simulation fundamentals with regards to caustic treatment and Merox units. For our first-time attendees, just wanted to recap the philosophy and mission statement with Bryan Research and Engineering and how we operate amongst all our customers worldwide. At the moment, we are serving over 600 companies globally, and we have offices in 3 regions, namely Texas for the North American and South American region, Czechia for our European customers, and Singapore for our Middle East and Asian customers. One thing to remember is that Bryan Research and Engineering is not just a simulation software company. We also pride ourselves to provide unlimited and free customer service and modeling services to all our clients. So if there is one thing I want everyone to remember at the end of this session is that our relationship is just getting started. We would want to hear your questions. We would want to receive your PFDs such that we can model those units for you on ProMax and ensure that your project requirements and targets are met. In short, customer service is our mantra, and we would want to work with you and build a relationship that lasts a very, very long time beyond this webinar. For today's session on caustic treatment and Mercaptan oxidation, we have 4 main objectives, and I would hope that at the end of the next 60 to 75 minutes, you are able to take home 4 unique objectives. 1, understand the unique interactions that caustic has with H2S and CO2, namely acid gas, and how it is different from its interactions with mercaptan. So there's a stark difference on how mercaptan interacts with acid gas and mercaptans, how caustic interacts with acid gas and mercaptans. And we will be trying to understand this difference and how those implications are going to be put in whenever we're designing such systems. Secondly, we will be also learning some fundamentals simulation-wise on how to model absorber units on ProMax. Specifically for this today's webinar, we will be focusing on caustic absorbers. We will also be learning how to model reactions or reactors on ProMax. For people who have attended our sulfur recovery webinar, you guys would have gotten a bit of a entry into how this is done on ProMax. But today we will be going a step further and seeing how we can incorporate conversion reactions on ProMax, and we will be specifically trying to incorporate Merox or Mercaptan oxidation reactions. And finally, we will also be seeing how to install very important analysis onto ProMax to understand a bit more about our process in terms of the ions or the salts that are being present or formed in the unit. So we'll be focusing on setting up an ionic info analysis on ProMax as well. So these are the 4 objectives that we will be trying to hopefully cover. And if at any point you have questions, please feel free to use the chat and direct the question to everyone so that the DRE consultants, apart from myself, can also take a stab at those questions. However, just to ensure that your learning is maximized, I would probably encourage you to keep your questions towards the end of the session. We will be having around 15 to 20 minutes of Q&A so that you can ensure that your learning experience for the next 60 minutes is undisturbed. All right, so let's get started. Fuel or fuel gas in any system or any operating plant around the world needs to meet certain specifications before it can be sent to end users for consumption. So far, in the last 6 to 7 webinars, we have focused on how we can reduce the water content to acceptable levels. We did that through the hydrate suppression webinar. We also saw how we could remove H2S and CO2 to appropriate levels to prevent corrosion and environmental implications. And we did that in the webinar of amine sweetening. We also saw how we can bring down our fuel heating value or dew point conditions or delivery pressure conditions to the NGL fractionation train and a demethanizer webinar. Today, we will be focusing on the next set of contaminants which can make its way to fuel gas or any kind of fuel, even liquid fuel, and how we can treat those contaminants. So today's focus is going to be on the next set of contaminants, namely mercaptans. And the most common treatment that is used around the world to treat mercaptans is caustic treatment. So we're going to focus today on removal of mercaptans. On ProMax, as you guys would have seen over the last few webinars, or even our existing customers who've been using ProMax for a whole bunch of years, you might be aware that ProMax has a bunch of solvents available in its database for handling any kind of unit operation, specifically with regards to removal of contaminants. We have the generic amines, primary, secondary, tertiary. We have proprietary amines from Huntsman, Dow, or Shell. We also have physical solvents such as DEPG, NMP, propylene carbonate, methanol, sulfolane. We have potassium carbonate as well, which are employed in certain operations around the world. However, today's focus, as I've reiterated, is going to be on usage of caustic, which is basically a solvent that mixes NaOH around 10 to 20% with water. And as we have discussed in the previous slide, caustic is majorly used for the removal of obviously small amounts of H2S and CO2, but majorly sulfur components and mercaptans. And we will be seeing how that can be modeled on ProMax. All right. One of the major objectives that we discussed that we would want to cover in this session is to understand the difference of how caustic reacts with acid gas and mercaptans. All right. Caustic, in summary, can handle and treat both acid gas and mercaptans. However, both these contaminants interact very, very differently with NaOH. So let's focus on the left-hand side of this table. The handling of caustic with regards to acid gas. Caustic, while it can remove acid gas, it is a non-regenerable absorbent for acid gas. Now, what do I mean by that? When acid gas makes its way and gets removed by caustic, it results in the formation of heat-stable salts, such as carbonate, bicarbonate, or sulfide and bisulfide salts. This results in your caustic getting spent, and therefore, you will always require a fresh source of caustic being fed into your system. So there is definitely a loss in your system because of these heat-stable salts that are being formed. And you would always need to invest in incorporating a fresh stream of caustic to ensure that the spent caustic is made up for. All right. So in summary, the caustic can remove acid gas. However, it is non-regenerable when it comes to acid gas removal. And therefore, you need to put in some fresh source of caustic for every cycle. Now, that's not the case with caustic and mercaptans. Caustic can also remove mercaptans. However, the reactions of caustic with mercaptans are regenerable. Caustic can be regenerated using both thermal and reactive means, and therefore, it is a regenerable absorbent for mercaptan removal. As you can see on the right-hand side of this table, there is an oxidation reaction which I've put in. And basically what happens is if we oxidize, if we send in a stream of air into a reactor and we oxidize the mercaptans that have been absorbed by caustic, it can get converted into something called disulfide oils, all right, based on the reaction that I've mentioned. This disulfide oils forms a third phase. So usually in your caustic system, after you have contact your caustic with your sour fuel that enters your system, you would be having a liquid, an aqueous phase in your rich caustic stream. However, when you react the mercaptans with oxygen, a third phase, or the oil phase, hydrocarbon phase, starts forming. And with the help of a three-phase separator, we can decant out this oil layer, which allows us to recycle or regenerate back the aqueous caustic solvent back to our contactor. So what you can see is that caustic is fantastic for both H2S, CO2, as well as mercaptan removal. However, with mercaptans, we have the luxury of regenerating our caustic. With acid gas, we do not have that luxury. Now, in the industry, the oxidation of mercaptans to form this disulfide oil layer, followed by a three-phase separator to decant out this oil layer, so that you can regenerate back your fresh aqueous caustic, is commonly called as a Merox unit. It's the short form for mercaptan oxidation. All right, so today's focus will be on Merox units. However, please remember that there is another way to regenerate your your caustic through thermal means. However, we won't be focusing too much on those systems because those are not as commonly seen in the industry. So we'll be focusing on the oxidative regenerative systems today, and how with the oxidation of mercaptans we can regenerate our caustic. On this screen, you can see a standard Merox unit. This is a simple PFD of a Merox unit, and I would like to split up this flow sheet into two sections. The first section is the caustic contactor, which is my methyl mercaptan removal contactor here. Again, I've just put it as methyl mercaptan, but you can have whole sets of mercaptans available in your feed. It can be methyl, ethyl, propyl, butyl, pentyl, any sorts of mercaptan, but your first section of this unit is focused on the mercaptan removal through a contactor. All right, and in this contactor, what is basically happening is we are having my sour fuel that comes in from the bottom, my fresh caustic that comes in from the top, and if your tower is designed well, your acid gas and most importantly your mercaptans should make its way into the rich caustic phase. All right. Then, to ensure that you can regenerate your caustic, we send in a stream of air. So your air and your rich caustic stream are together sent into a Mirox reactor. The Mirox reactor is the reactor where you will be carrying out the reactions which I showed you in the previous slide, which is basically mercaptans plus oxygen gives you disulfide oil plus water. After the reaction, once you form the disulfide oil, you have to drop the pressure such that you can decant out this oil layer. Any vapor phase that is formed due to the dropped pressure is vented out, and then the aqueous caustic can be regenerated back into the caustic tower. It's a very simple setup. And again, the two parts are number one, the caustic contactor, and number two, the mercaptan oxidation reactor or the caustic regeneration system. There's a question by Mr. Yogesh Jain on WebEx. What are some other methods to regenerate caustic other than Merox? The other method commonly used, but again not as popular as Merox, are thermal regeneration systems. So you can just inject some amount of steam by taking in your rich caustic into a tower, injecting some steam, and hopefully that steam can remove all your disulfide, can regenerate your caustic by removing any excess mercaptans that have been absorbed. Again, today's focus will be on mercaptan oxidation. However, the example files on ProMax gives you certain cases of how thermal regeneration of caustic can also be taken care of. All right. Now let's go through some KPIs of the caustic treatment and mercaptan oxidation setup. The first KPI is your product spec. Your product spec, again, needs to be less than an industrial average, and usually we have seen around 75 ppm per volume of sulfur should be present in your sweet fuel gas or liquid fuel. So you need to ensure that your unit is designed in such a way that you have less than 75 ppm per volume of sulfur. The second KPI is to ensure that you have less than 200 ppm of acid gas in your inlet fuel stream. If you guys remember from the previous slide, there is certain disadvantages in the mercaptan and acid gas removal. And namely, I'm again reiterating this, mercaptan handling with acid gas is non-regenerable. So if you're going to have high concentration of acid gas entering your caustic unit, you're going to have large amounts of spent caustic, and then you're going to have large amounts of fresh caustic to ensure that your system is always made up and always that your spent caustic is having some amount of makeup associated with it. So to prevent such a loss in your system, we need to ensure that your acid gas in your feed stream is less than around 200 ppm. If there is any situation where there is more than 200 ppm of acid gas in your stream entering the caustic unit, we would encourage you to either have a pre-wash system so that you can remove your acid gas, or you can ensure that your acid gas is removed through an amine unit. All right, but please ensure that you have minimal amounts of acid gas entering your caustic unit just to prevent the makeup of fresh caustic again and again. The mercaptan extractor itself, the tower itself, if you're trying to sweeten or remove mercaptans from a liquid fuel, ProMax has the capability of modeling LLE towers, and usually LLE towers are packed. We have commonly seen a ratio ring packing around 10 to 12 meters that are usually installed around the world. If you're trying to remove mercaptans from a vapor fuel, then again, we have the capability of VLE towers on ProMax, and anywhere around 2 to 4 idle trays or 6 to 10 actual trays should do the trick for you. Again, these are very short towers, and just because of the basicity associated with caustic, short towers should do the trick. So LLE towers, usually ratio ring packings, 10 to 12 meters tall, and VLE towers around 2 to 4 idle stages or 6 to 10 actual. Fresh caustic needs to be put into your system. As I said, if there is H2S and CO2 in your feed, that will continuously result in the formation of heat stable salts, and that will result in spent caustic. And to ensure that you're always making up that lost caustic in your system, some amount of fresh caustic needs to be constantly put into your system, and that is a disadvantage with caustic handling of acid gas. Usually the flow rate of the fresh caustic stream is around 0.1% of your actual recirculation rate of caustic in your system. So if you're having 50 gallons per minute of caustic being circulated in your system, 0.1% of that should do the trick for your fresh caustic to ensure all the spent caustic is made up in your system. Again, this is only necessary if you have H2S or CO2 in your feed, not necessary when you have mercaptans, because mercaptans and caustic results in complete regeneration of caustic without any issues. Your lean caustic in your system, again, less concentrations. Usually we have seen around 20 weight % or less than that, and very small flow rates. I would always start off with 5 gallons per minute, 10 gallons per minute, but nothing in the ballpark of 3 digits. We've modeled a number of caustic units around the world, and just based on the weighted average, anyway, a good starting point would be 5 to 15 gallons per minute. Again, that's the advantage of a simulator. You can always start off small and then play around with various tries and tribulations and see where you reach. But a good starting point is around 5 to 15 gallons per minute just to get the simulation started. The rich caustic stream that comes out at the bottom of your Mercaptan contactor, again, as I said, this is going to be the topic that's going to be reiterated multiple times during this webinar. You do not want too much of your heat stable salts being formed in your rich caustic stream, because more and more amounts of heat stable salts being formed, that's going to put more load on the fresh caustic stream that needs to be input into your system to make up that loss. So usually we have a rule of thumb for the amount of sulfide salts that can be formed into your rich caustic stream. And a good KPI for that is around 0.28% of sulfide salts. If you're more than that, then you know that you have too much of your H2S or CO2 coming into your stream. And therefore, based on KPI number 2, you need to install some kind of pre-wash system to reduce the acid gas feed into your tower. All right. And one of the objectives which we discussed at the beginning of the webinar is to see how we can calculate the amount of salts in your rich caustic stream. So I will be coming on how to do that on ProMax in a second. Just remember, you do not want high amounts of heat stable salts in your rich caustic stream. So we have completed the caustic contactor part of the system. Now we come to the second part, which is the Merox part, to regenerate my caustic. And as I said, there are multiple ways, either through thermal means or oxidation means, and today's focus is going to be through oxidation means. So if we inject some amount of air to the oxidative regeneration reactor, we should hopefully be able to complete the Mirox reaction. So how much air should be used? Usually our recommendation is 10% excess than the amount of mercaptans entering the system. So what do I mean by that? If you can double click the inlet fuel, the inlet sour fuel, and figure out how many moles of mercaptans are entering, then you would know how many moles of oxygen is required based on the reaction that we showed you in the previous slide. So through stoichiometry, just sum up the mercaptans flow in your inlet stream, divide that by 4 based on the balanced reaction, divide that by 0.21 to get the actual moles of oxygen, and then multiply that by 1.1 to give you 10% excess. As simple as that. All right, so that would be a good starting point for how much air is required for your Merox reaction. Coming to the Merox reactor itself, as I have put in the reaction that we would want to take place in the system. If you can see, the balanced reaction would show you for 4 moles of mercaptans, we have 1 mole of oxygen. For 2 moles of mercaptans, we have half moles of oxygen. All right. I will be showing you how to incorporate this reaction into ProMax in a second. But just remember that this reactor is a 3-phase reactor because you will be having the formation of the disulfide oil layer, which is a new phase that is going to be formed. So you have to ensure that 3 phases are selected in modeling this reactor and not 2 phases. All right, that's the key thing to remember here. After your Merox reaction has taken place, you would have a 3-phase separator to separate out or decant out the disulfides. Usually a pressure drop of around 30 pounds is what we have seen usually around the industry. And what that would do is it would just take in your mixed liquid stream from the reactor, drop the pressure, and separate out your oil layer from your aqueous layer. And if any vapor is being formed, that can be vented out as well. Many times in the industry, we have also seen some fresh amount of naphtha or any crude cut being injected into your 3-phase separator as well. What this does is it removes any trace amounts of disulfide from the aqueous layer and pushes it back into the hydrocarbon layer. You would not want your disulfides to be circulating in your system in your aqueous phase. So to push it from the aqueous to the hydrocarbon phase, we have seen many a times companies inject some small amount of naphtha or a crude cut to remove those trace amounts of disulfides from the aqueous caustic phase. So that can also be modeled on ProMax. Finally, we have a circulation pump because you will be having a 3-phase separator upstream, which would have dropped the pressure of your system. And just to ensure that your lean caustic now can go back into your contactor, we need a circulation pump to bring back the caustic pressure high enough to be fed into the scrubber. All right, so these are 10 important design considerations that we would need to take care of in setting up such simulations on ProMax and designing such systems with the help of ProMax. Before I open up ProMax, let me just go through a few questions that have come in. And if I can answer them, I would answer them right now. Otherwise, we can always take them offline. So I see there are certain questions of how much naphtha can be used to remove your disulfides. Again, there is no real rule of thumb for how much naphtha can be used. My answer to that would be that's why we have a simulator. You can always start off with small trace amounts of small flow rate of naphtha and see whether that's doing the trick. If not, increase your naphtha feeding into the system. Again, there is a cost benefit analysis associated with this. Putting in more amounts of naphtha would reduce your CDU throughput, because you do not want to remove so high amount of naphtha from your products. So again, I would say use the simulator to its advantage. We have all the equilibria and thermodynamics for you, but I would say a very, very small flow rate should be the starting point. All right, so at this point, let me open up ProMax just to show you guys how a Merox unit can be modeled. Can I get the BRE consultants to confirm that they can see the ProMax screen? All right, I think everyone can see the screen. So I've just redrawn the Merox system again on ProMax, and let me go through step by step what a BRE consultant would do in setting up the simulation, so that you can get a real vicarious understanding of how the system is set up. Step number one with any new simulation on ProMax is to activate your environment with the appropriate thermodynamics. So how do we do that? Step one is to click the active environment on the top left of your screen. After you click that, you should see a active environment window appear. And again, selecting the most appropriate thermodynamic package is probably 50% of your battle won. If you do not select the right package, you're going to face a lot of issues in getting appropriate results. Now, ProMax, since we are leaders in sour fuel handling and sour gas treatment and everything associated with acid gas and sulfur, we have proprietary packages concerning various units handling these contaminants. If you're modeling an amine sweetening unit, we have the amine sweetening package. If you're modeling a caustic treating package or a Merox unit, we have the caustic treating packages available here. If you're modeling a sour water stripper, we have the electrolytic packages available right here. If you're modeling a sulfur recovery unit, we have the sulfur packages available at the bottom. So depending on which kind of unit you're modeling, you can use the appropriate package. If there are any trace amounts of polar components that are coming in, you can also use the SRK polar or Peng-Robinson polar package that is available on ProMax. All right, so for now, in this case, I have selected the caustic treating package for usage in this simulation. Next step is to ensure that all the components have been added in to ProMax. First step is obviously to ensure that all the components present in my sour fuel are put in. So I've put in all my hydrocarbons, my mercaptans, my acid gas, if any. However, please remember that since these are reaction-based units, you also need to put in the reactants and products that will be part of your Merox reactions. All right, so if you remember, mercaptan needs to be reacted with oxygen in your Mirox reactor. So you need to also add in oxygen in your environment list. All right. And actually, if you're trying to be very, very accurate about it, you would want to add in air, and then air would react with your mercaptan stream to complete the Merox reaction. So I'm going to put in nitrogen, argon, and oxygen to make up my air stream, and so that that air stream can react with my rich caustic stream. So I've added in all the components that make up air. The product of my Merox reaction are disulfide oils. So please remember that apart from your original mercaptans that have been added into your environment, you need to add in the corresponding disulfide oils. In this particular case, I have only methyl mercaptan in my feed stream. So the corresponding disulfide oil is dimethyl disulfide, or also known as DMDS in the industry. If you have ethyl mercaptan, you would add in DEDS as well. All right. So depending on which mercaptans are in your sour fuel, the corresponding disulfide oils also need to be added. And that's the advantage of ProMax. We have the presence of all the corresponding disulfide oils vis-a-vis the original mercaptans. And again, you do not need to add any salts. ProMax will take care of the salt formation for you because we have selected the appropriate package, and the ionic info analysis will take care of those salts. So just remember to add in your feed stream components, your reactants, which is air, namely nitrogen, oxygen, argon, and your products, which are the corresponding disulfide oils vis-a-vis the mercaptans that are coming into your stream. All right. In this case, only methyl mercaptan is there, so I'm only going to add dimethyl disulfide. All right. I can then click OK and ensure that everything is selected. All right. So now, if you can see, I have a sour fuel stream coming in. It has around 1500 ppm of methyl mercaptan, and it's a very small amount of H2S. And if you remember, the rule of thumb we said was to have less than 200 ppm of acid gas. So we are fine here. We do not have high amounts of H2S or CO2, but we are considerably over the limit for mercaptans, given that our sweet fuel should have less than 75 ppm of mercaptans. So therefore, there is a need to have a caustic system. All right. So step one is to put in some amount of caustic flow and caustic composition. And again, the rules of thumb tells us to start small. Always start small. It's better to be, to start small and then ramp up your system than to start big and then figure out, hey, I would have missed out probably a much more conservative result previously in my simulation. So start small is my suggestion to all users. All right, so caustic composition, let's say a small concentration of 20 weight percent. So I just put in 20 weight percent of caustic. Let's put in a small flow rate of say 5 gallons per minute. And if you remember, since there is small amounts of H2S coming in, it's not huge, but we can't neglect the fact that there is small amounts of acid gas, namely H2S coming in. It would be wise to put in some fresh caustic because H2S will result in the formation of sulfide salts, and sulfide salts are heat stable, and therefore to make up for those spent caustic, some fresh caustic should be put in. And if you put in the rule of thumb by PRE around 0.1%, I can put in say 0.005 gallons per minute of fresh caustic. All right, so far so good. We've put in the composition of my caustic. I've put in my caustic flow rate and my fresh caustic that needs to be put in to handle the sulfide formation. Then what I like to do at this point is I can use my mouse just to select the contactor part of my system and just execute block to ensure that everything is working fine in my contactor and my mercaptans are being removed. We can take care of the Merox unit in a second, but just select those contactors and my lean caustic stream and ensure that everything is working fine in my contactor part. You can see that my mercaptans are getting reduced from almost 1500 ppm to 13 ppm, which is good to see. All right. Now we have to remove, beg your pardon, we have to react my mercaptans with oxygen so that my disulfides are formed and I can separate that out into the oil layer and regenerate my caustic back to my mercaptan tower. All right. And for that, first things first, I need to put in some amount of air. And if you remember the reaction I've put in here, for 4 moles of mercaptan, I would need 1 mole of oxygen. So if you double click my sour fuel, and go to the composition tab and go to the molar flow tab, I can quickly go and see that I have around 2.4 pound moles per hour of methyl mercaptan. All right. So if I now quickly take up a calculator, so 2.4 moles divided by 4 would give you the amount of oxygen, divided by 0.21 would give you the amount of air, And if you have 10% excess, I can multiply that with 1.1. So a good starting point is around 3.14 pound moles of air. I hope everyone's clear on how I got this amount of air for my Merox reaction. So I can just go into my air dashboard and let's put in 3.2 pound moles of air. All right. So let's proceed. We have put in my airflow. My rich caustic is coming in, and now let's go to the Merox reactor. If I double click my Merox reactor and just increase the screen, you can see that we have been asked to make few selections. The first selection is the type of reactor. All right. And if you drop down this menu, you can see that there are many kinds of reactions available. We have the equilibrium type, we have the conversion type, we have the Gibbs minimization, upflow. For the Merox case, we will be using the conversion reactor. All right. If you guys remember from the sulfur recovery webinar, for the sulfur recovery webinar, we use the Gibbs minimization reactor because ProMax already has the required Claus reactions, subdew point reactions, burning reactions, redistribution reactions already inbuilt for SRU units. Just because there are different kinds of mercaptans involved and different oxidation reactions involved, we have not done that for Merox reactions. So you have to manually put in those reactions. Again, I would like to reiterate that Gibbs minimization might work for methyl mercaptan, but if you have heavier mercaptans like ethyl, propyl, or butyl mercaptans, we would not encourage you to use Gibbs minimization. I know you guys might be tempted to use Gibbs minimization because you do not need to put in any reactions, and ProMax does all the work for you based on least Gibbs energy in your product stream. But just to be thorough and complete, we will be incorporating the reactions manually, and specifically we'll be adding in conversion reactions. Now, if you drop down the reaction set, you will have certain reactions that you can add in, but let me show you how to add those reactions from the scratch. All right. So if you have a fresh ProMax screen, how would I add these reactions? On your project viewer, on the left-hand side, you can see that there is something called the reaction sets. All right. And in the reaction sets, what I would do is I would just right-click my mouse and I can click add. All right. Let me name my reaction set as reaction set for Mercaptan Oxidation. I always like naming things so that we are aware about what kind of reaction sets I'm adding into my system. All right. Once I've added in the reaction set, I can click new. All right. And it will ask me how to configure this reaction. All right. So let's name my reaction 1 in this reaction set as methyl mercaptan to dimethyl disulfide. Again, please name all your reactions because again, if you have multiple mercaptans, you will have those many oxidation reactions. And if you don't name it, you'll get confused as to which reaction belongs to which mercaptan. So in this particular reaction, I'm going to name it as methyl mercaptan to dimethyl disulfide oil. That's step 1. Step 2, I would add in all the components involved in the reaction. And if you guys remember the reaction, it will be methyl mercaptan plus oxygen gives you dimethyl disulfide plus water. So I can just select my components. I can either select my drop-down menu and find the components. However, everything on ProMax is VBA enabled, so you can still type in the components and do the trick for you. So let me add in my first reactant, which is methyl mercaptan. That's added in. The second reactant is oxygen, so I add that in. My first product is DMDS oil. Add that in. And my second product is water. All right. Hopefully, so far, everything is quite intuitive. Then I need to put in the stoichiometry involved in the reaction. And if you remember, again, from the slides, which I will be sending every one of you, I'll be sending the slides as well as the ProMax model for your reference. The stoichiometry is 2 moles of methyl mercaptan with half mole of oxygen gives you 1 mole of DMDS and 1 mole of water. So to put it into ProMax, I would put a negative sign for my reactants and a positive sign for my products. As simple as that. All right. Then I go in to the type of reaction that I want to put in. So again, the type of reaction that I want to put in is a conversion reaction, and I would be interested in the complete conversion of methyl mercaptan to DMDS. So in my left hand side section, I would scroll all the way down to the conversion equation. I can skip equilibrium and rate constants because I am not interested in those reactions. I'm interested in setting it up as a conversion reaction. My conversion base is methyl mercaptan, so I drop down the menu and click methyl mercaptan. And I'm interested in the complete conversion of methyl mercaptan. So based on the conversion equation, which we have studied in the university, I want a complete conversion of methyl mercaptan. So I've put my coefficient for A as 1. All right. And that's it. I can then click OK. And my reaction has been configured. It has not been set up in my environment. It has been configured. After that, ensure that you have selected that this reaction is a conversion reaction here. I am not interested in equilibrium and kinetics, so I can deselect that. And now I'm ready to activate the first reaction, which is methyl mercaptan to DMDS. Now, if you have multiple mercaptans, you have ethyl mercaptan, you have propyl, butyl, pentyl, you have to add in those many reactions, and you would follow the same steps. All right. Add in your reaction by clicking new here, put in your reactants and products, put in the stoichiometry, ensure that you have selected complete conversion through the conversion equation, and then activate your reaction only for the conversion reaction. That's it. All right. And I can close out from this window. And now there's one more small step in the active environment section, which we saw in the beginning of the ProMax demonstration. After you select your package and your components, all the way at the end, there is a reaction set tab. So you have to select that. And you have the reaction set for mercaptan oxidation available now. So if once you have configured it, you have activated it, the final step is to install this reaction set into your environment. So I can select this and install it into my ProMax environment. And once it is installed, you can click OK. And hopefully now, once I double click my reactor, under reaction set, you should see the new reaction set that has been installed right now. Reaction set for mercaptan oxidation. And that's why I always encourage everyone to name your reaction sets, name your reactions so that you're aware of what you're adding in and what you're not. So now I can drop down my menu and click my reaction set. So just to kind of give you a bird's eye view of what this is, a reaction set is a set of multiple reactions. Within the reaction set, I have only added in one reaction, which is methyl mercaptan to DMDS. A reaction set can have multiple reactions. So if you have multiple mercaptans, I would add those many reactions under that reaction set. So selecting this reaction set would enable all the reactions to participate in this particular block. So hopefully I've made that myself clear in that. Finally, make sure that the maximum phases of this reactor is 3. By default, if you install a new reactor on ProMax, it would show 2. But as we've discussed through the presentation, there is the formation of an oil layer, a hydrocarbon layer, and therefore please ensure that your maximum phases is selected to 3. All right. You can play around with the pressure drop and bypass fraction if you'd like, but just for demonstration sakes, I'm going to leave it at 0% for now. Bypass fraction, for those who are interested, is just to ensure how much of your reactants are not going to participate in the reaction at all. So if there is some inefficiency associated with your reactor and your vendor tells you that there is only 99% of reaction possible, I would put in a bypass fraction of 1 to 2, and that would add in that level of conservatism to my reaction. But again, for demonstration purposes, I'm going to leave it at 0. All right, so I have configured my Merox reactor, and now I have everything set up. I've already put in my pressure drop for my disulfide decanter, a pressure change for my pump, and I can go ahead and click execute flow sheet. This will take some time to converge, and while it is converging, I would probably just answer some questions that I can see on both WebEx and Zoom. One question that I've been asked is, can we model a pre-wash system in order to remove small ppms of carbonyl sulfide and H2S? Absolutely, you can. Any system which involves caustic pre-wash, amine pre-wash, any kind of water wash as well, all of those systems can be modeled on ProMax absolutely fine, no issues. Yes, there's a question on, can caustic remove carbonyl sulfide and carbonyl bisulfide? Absolutely, it can remove those as well. And I think many questions are around whether we will be sending the presentation slides. And my answer to that is, again, yes, we will be sending everyone the slides as well as the ProMax model fully converged with all the reaction setup for your reference. So you guys do not need to worry at all about, how to do it from scratch. All of this will be sent to you guys. There are some questions on how I added the reaction on ProMax. I hopefully, through my demonstration, you guys were able to pick that up. Clicking any stream on ProMax, would give you the project viewer, and the project viewer would have your nice file explorer on the left-hand side. And if you can see on the left-hand side, all the way to the bottom, I have my reaction sets. All right, and just right-click this reaction set, and you can add your new reaction set. So I will be showing this in a second. All the heat stable salts will be automatically taken care of within ProMax. And again, if you double click any stream on ProMax, either the spent caustic stream or the rich caustic stream, you should be able to see, I will show it to you in a second, how we can configure an ionic info analysis, and also how we can configure to check the amount of salts, specifically heat stable salts that are being formed. And at any point of those heat stable salts are beyond our level, then you can take the required steps by adding in some fresh amount of caustic or increasing your flow rates to ensure that that is taken care of. Or as I always like to suggest, installing some amount, a pre-wash system upstream of your caustic tower also do the trick. All right, any other questions? I think I've answered most of them, but again, we will be staying back for about 15 minutes after the session. All right. Now we have a converged Merox unit. And now let's see how we can analyze the system. A green simulation does not mean it is correct. A green simulation just means that it is converged. How do we ensure that everything is correct? I think the most important way to start your validation of this model is to check whether your Mirox reactor is forming disulfide oils. So I would double click my Mirox reactor. And how I like to check is I can go to my streams tab on the top. I can go to the composition sub tab. And under my drop down menu, just select molar flow. If I zoom in, you can see that in the inlet, I have around 2.4 pound moles per hour of methyl mercaptan. And in the outlet, it becomes 0 because it is getting converted into disulfide oils and water. So that makes sense. And my Merox reactions are taking place perfectly fine. In my 3-phase separator, because of the pressure drop, I would want my mixed liquid stream to be decanted into 3 phases, namely vapor, oil, and aqueous phase. And I would want to ensure that maximum amount of my disulfide oils are present in my hydrocarbon phase. So if I double click my separator, I can go to my streams tab again, go to my composition tab. All right. And you can see that in my disulfide oil layer, almost 98% of my dimethyl sulfide is getting decanted out. So that means that my separator is also working just fine. All right. And my aqueous stream, which is my stream number 26, is, if I go back to mass fraction, is having 21.8% of caustic and 75% water, which is good enough to regenerate back into my Mercaptan contactor. So my regeneration Merox system is working just fine. My reactions are working fine. Therefore, I can be very well assured that the amount of air that I've put in was stoichiometrically sufficient, and my caustic is getting regenerated back. Now, a few things. If you guys remember, there were a few KPIs with regards to heat stable salts, which we have to make sure that we are not exceeding. So how do I set up that analysis? I can double click my rich caustic stream. I can go into the analysis tab. And right now I already have the ionic info analysis set up. But for people who do not know how to set this up, I can just demonstrate that for you. Go ahead and click add analysis. And when you add analysis, there should be an analysis called ionic info analysis right in the center. You can click OK. You can go ahead and click solve. Once you click solve, I like going to the second tab, the salt composition, and you can see right at the bottom all my carbonates, my sulfide salts, and their respective concentrations available. All right. So if I check my sulfides, which are the last two, you can see that the concentration is around 1.5 and 0.01%. If I check my carbonates, you can see that it is 4.63 and almost and 0.0014%. If I can do this analysis on the spent caustic stream as well, that would be a good good analysis, right? Go ahead and click analysis, click solve on the ionic info analysis, salt composition. You can see that the spent caustic stream is having around, again, the same amount of sulfide concentrations and the same concentration of carbonate. If at any point you would want to reduce these heat stable salts in your system, all right, the knob that you would want to change would be your fresh caustic stream. All right. So again, we have certain recommendations of how much sulfides we would want in your spent caustic, and to ensure that that is reduced, you can always play around with the fresh caustic stream right here. Again, it really depends on what your end user wants. And if you're an operating company yourself, it would depend on your cost benefit analysis. Are you willing to invest in a pre-wash system to remove those H2S and CO2 upstream, and then you do not need to worry about heat stable salts in a caustic unit? Or are you willing to invest in a constant inflow of fresh caustic to prevent that buildup of heat stable salts? So it really depends on what your requirements are and what your constraints are. But that's how I would select or configure my analysis to calculate the amount of carbonate and sulfide salts present in my system. How can I size my tower? Well, if I have to size my tower, I can just go ahead and double click my tower right here. As I said, Mercaptan towers are usually 2 to 4 ideal stages, or if you're doing actual stages, that would mean around 6 to 9 actual stages. And sizing it is, again, very, very simple on ProMax. I would double click into my tower, go into process data. First things first, select which mode you want to model your tower on. I've done it on ideal stage mode, but feel free to do it on mass and heat transfer mode as well. The only difference is that on ideal stage mode, you would be using ideal stages. Therefore, you need to ensure that you have some amount of efficiency taken into consideration. And for absorbers, again, anywhere between 25 to 35% efficiency is a good, good rule of thumb to follow. And if you're on the mass and heat transfer mode, put in the actual number of stages. Anywhere between 6 to 9 should do the trick for you. Now, if you want to size your Mercaptan tower, I would go to hardware section under general. All right. And again, if you want to size it, put in a target flooding that you would want in your tower. I would want a 75% flooding in my tower on both my stages. I would want to be conservative and give my real to idle stage ratio to be 4, which corresponds to 25% efficiency. And a system factor is the tendency of foaming in a caustic tower. Again, usually BRE recommends around 0.65 to 0.75 as the system factor for caustic towers. If at any point you are not able to remember this value, you can always go back to our help file, which is an encyclopedia of anything chemical engineering, and type in system factor. And you can see this will help you in sizing any kind of tower with any kind of solvent that you're using. So if you're using a caustic wash, around 0.65 system factor is what we suggest. If you're using an amine contactor, those recommendations are there. Sour water strippers, glycol contactors, CDUs, VDUs, so on and so forth. All right. So for my caustic tower, I'll just put in a system factor of 0.65. All right. So I've put in my general hardware information targets that I would want. And remember, I'm sizing this tower, so I've put in a target flooding so that ProMax can give me the diameter. If I am rating my tower, I would put in the diameter so that ProMax would calculate my flooding. And another important point at this stage is that I have selected my hardware to be tray. I can change my hardware to be either random packing or structured packing, depending on your requirements. Since I've selected tray, I go into my tray folder right here and give it some more information with regards to tray spacing and wear height information. You can also change the tray type from sieve to round valve, depending on your requirement. But I'm just going to put a usual with tray spacing, which I see in the industry, around 0.5 meters for both my trays, wear height of around 3 inches, and leave the remaining values at the default suggestions by ProMax. And then when I go back to my general settings, I can click solve, make this into meters, and ProMax gives me around 1 meter as the size of my Mercaptan tower. Right, so this is how I would size my Mercaptan tower, as simple as that. One small note at this point is that if you can see, the flash type for this tower is selected to be VLE because my sour fuel is in vapor phase. If you're trying to remove mercaptans from LPG or from a liquid fuel stream, you should not use the VLE flash type. You would have to drop down this menu and select the LLE flash type, because you are not having vapor entering your system. You're having 2 liquid streams entering your system. So in those cases, when you're having a liquid fuel that needs to be treated, please ensure that you are at LLE mode. Otherwise, VLE is absolutely fine. There you have it. This is how I would set up a caustic treating and a Merox system on ProMax in no time. We have completed the session at this point. So I would like to say a few things for people who would want to leave at this point, and for people who would want to stay back and ask questions, feel free to do that. But for people who are wanting to leave and carry on with their day, I would like to thank you for attending our short webinar on caustic treating and Merox units. I hope you were able to gain something from this session. Again, we would want you to send in your questions, your PFDs and your HMDs to get these units modeled for you on ProMax. We have the best packages, thermodynamic capabilities to handle all these sour and sulfur systems. So please ensure that you're sending in your requests and getting those ProMax models built. There is no charge associated with building these models. And again, if there's one thing I would want you guys to take away, is that our customer service is complimentary for all our customers. So with that, thank you to all our existing customers and prospects who have come in. Have a good day. And for people who would want to stay back, we will be here for the next 15 to 20 minutes to answer any questions that you might have. Thank you. All right, so there's a question on this makeup blowdown block and how this is set up and what is the purpose of this block. So the makeup blowdown block is a ProMax specific block, which is to induce steady state into our system. ProMax is a steady state simulator. We are not yet a dynamic simulator. And therefore, to ensure that your model is at steady state, we have this makeup blowdown block. And again, this makeup blowdown block at any point, if you're having caustic that is getting spent, will be blowed down from a system, because I would always want to ensure that my target of 20% is being met. And this fresh caustic stream that I've set up based on my rule of thumb is doing that trick for me. So the spent caustic is just to ensure that my steady state is being maintained in my system, and the fresh caustic stream that is being added in is making up for that loss. All right. And I'm having a direct control over this fresh caustic stream based on the rule of thumb that I have set up. Yes, this tower can also be modeled as an LLE tower. As I've shown, if you want to model an LLE tower, you can double click your tower here, and under flash type, you can drop down this menu to select LLE for any sour liquid streams that needs treated. Just to clarify, all the units involved in this system, be it the contactor, the heat exchanger, the separator, can be sized on ProMax. We did a short webinar on Monday going through that. So even your lines, for that matter, your pipelines, your rich caustic lines, your lean caustic lines, all of these lines can be sized. And again, if you have any questions on how to size, please reach out to us. We will be more than happy to help you to size those units. The reactors on ProMax can also be sized, but again, it's not as intuitive as our heat exchangers and columns and separators. It is, as my colleague Joachim said on Zoom, it is more an art than science. You have to play around with the aspect ratio of your reactor, which can be done by double clicking the reactor. Under process data, under hardware, you can take care of this area here. Again, I'm not going to go into the details of how sizing is done, but you have to basically ensure that your pressure drop that is calculated on ProMax is not going overboard than what is recommended for your reactor. All right, so please send in your questions regarding sizing, and we can do that for you. Again, more on it will take a bit of collaboration between both of us to ensure that those sizing requests are put in. The help file, yeah, absolutely. The help file is very, very comprehensive, and all our customers who have the help, who have ProMax installed, you guys can read tons and tons of process engineering related information on our help file. It talks about design suggestions, optimization suggestions. It even goes into how to set up various things on ProMax, various popular process units like SRU units, caustic units. You can just go ahead and click whatever you want to talk about. Like if you are interested in caustic units, you can click caustic units, and it goes through all the details, both process related and simulation related, of how you would want to set it up. So again, a simulation database of a lot of information, as well as engineering database for designers and operators to keep reading. So LLE towers on ProMax are sized slightly differently as well than regular VLE towers. How I would model LLE towers is, I can maybe show it to you guys. Right now, obviously, we're having vapor coming into our system, but let me just take out another tower and see if I can show you guys. All right. So I'm just taking out another tower here. And if you have to model or size an LLE tower, if you double click my tower, you can select this to be LLE. All right. However, the minute you select LLE as your flash type under hardware, most of the inputs that were available on VLE towers are grayed out. So how do we size LLE towers? Now the recommendation for LLE towers is around liquid load. And usually, based on our experience, we've seen that the liquid load in LLE towers should be less than 30 GPM per feet square. All right. So you do not have the flexibility of putting in fraction flooding. You have the capability of putting in a liquid load. And so based on our recommendation, if you put in around 25 GPM per feet square on both stages, and when you click solve, right now I don't have any streams associated with it, but once you click solve, the diameter will be calculated for you for this LLE tower. So sizing an LLE tower is based on liquid load rather than fraction flooding. How does the oil quality affect the process? Is there any restriction about maximum sulfur or acid compounds? I am not sure who this person is because I can't see your name. It's, I think, your computer name that has been showing up. But anyway, yes, there is a direct linkage. Hi, Mr. Giovanni. So yes, there is a direct linkage between the quality of your oil that comes into your system and how it is going to affect your caustic and Merox unit. As I've discussed, if you're having high amounts of acid gas components coming into your system, that is going to result in the formation of heat stable salts. The formation of heat stable salts will result in the formation of spent caustic, and the formation of spent caustic would reduce the amount of available caustic to treat your mercaptans. Therefore, if you do not have fresh caustic that is continuously added into your system will definitely be affected. And again, as we discussed in the presentation, if you're having high amounts of H2S, CO2 in your feed, either remove them through a pre-wash system or ensure that your fresh caustic flow is high enough to make up for that loss. These vents can be sent wherever you would want, Mr. Manuel. Again, depending on the composition and the quality of these vent, you can use it for different purposes. If they are meeting environmental regulations, you can just vent it into the air. If they're not, you might have to incinerate it, and incinerators can be modeled on ProMax. So it really depends on what you would want to do with, depending on the composition of the vent, what you would want to do. In this particular design, I'm just venting it into the atmosphere, but you can burn it. You can send it to a fuel gas network if there is enough fuel, or again, depending on the composition, you can do whatever you want with it. There's a question as to when do we select ideal or when do we select actual trays? So again, Ahmed, the answer to that question is more so depending on at what stage of your process design or what stage of your project you are. If you are on an initial stage of your design, if you're setting up a fresh caustic system or a fresh Merox system, I would start off with ideal stages just so that I can have quick simulation results, quick thermodynamic results, and I'm good to move ahead in my project. If I have to validate my designs or if I have to debottleneck an existing process, I would select an actual tray system or a mass and heat transfer system. And when you're selecting actual tray system or mass and heat transfer systems, you have to be very assured that you have all the hardware information for your towers. And again, that can be answered depending on which stage of your project you are in. If you're early stages of your project or early stages of design, you really don't have much information about the tower in general. So you are forced to use ideal stage, and that's why we have that option. If you're on the later stages of your project, once your design is confirmed, once your plant is set up, go ahead with actual trays or actual hardware information, because you have your hardware sheets available and you can use the mass and heat transfer option on ProMax. So we have given both the options just so that all phases of your project and all engineers involved in all phases of the project have a good time using ProMax. It really depends on which stage of your project it is. Yeah. What is the O2 concentration in the recycled caustic? All right, let's check that. Let's double click the stream composition. It's close to 0. 6.3 into 10 to the 10 raised to the power -5. So it's close to 0. And that makes sense. You should have aqueous caustic circulating in your system. Like mass fraction, you can see 75% water, 21, almost 22% NaOH, and trace amounts of hydrocarbons and acid gas, trace amounts of that as well. All right. You should have all your gaseous components in your vent. So your nitrogen, oxygen, argon, some amounts of DMDS in your vent. Yeah, again, if you want to check in ppb, we can go double click the system, go to mole fraction, and you can just change these units to ppb. And you can get your ppb amounts right here. And again, if these values are higher than what are recommended by your systems, then you might need to play around with pressure drops, with flow rates of oxygen, so on and so forth. But you can always check as to what the composition of various components are in whichever units you would want. I am going to put in my email address in both the chats. So if anyone has any question, please email me, and I will be sending a blast email to everyone with the slides and the model. So you guys can respond to that email as well. Manuel, yes, as my colleague Joachim is saying, a mixer is not the same as a vessel. In a vessel, you will have equilibria being formed. You will have two phases being formed. So you would not want that. A mixer is just a node of two pipelines meeting. All right. Thank you for everyone who has attended our session today. It has been a pleasure to host all these webinars for you. And again, just to wrap things up, please ensure that if there are any questions that have been unanswered today, or if there are any clarifications that you would had on this presentation, please drop us an email. I will be sending the slides and the model to you very shortly, either late this evening or early tomorrow morning. And send in all your questions, be it process related or thermodynamic related, reaction related, and you should have a response from us very, very soon. And to all our ProMax users, please remember you are entitled to free modeling services from BRE. So if you want your Merox units modeled, all we will need is a diagram and your process targets, and we will be good to go.